The embedded blocks of RAM provided in the Spartan-3 devices each provide 18 kilobits of RAM or ROM storage. These blocks also have a reasonable degree of flexibility that you can exploit to lower costs. The block RAMs are fully synchronous. Data is written on a clock edge when the write enable is active. Data is read from a given address and transferred to the output on a clock edge. The port enable must be high for any operation to take place. Note that the data output N and data output P ports cannot be tri-stated. The synchronous set and reset port will reset the output register, but an initial value can be specified so that the output can be forced to any value. During a write operation, the output port can become the value that has just been written or the previously stored value at that location. You should also be careful of potential false timing paths caused by the relatively long delay resulting from reading data that has just been written to the block RAM. Each block has two independent ports, including separate clocks. There is no protection against writing to the same location from both ports, but your design should never attempt to do this. So here are a couple good tips. Use the block RAM for logical operations, like any ROM functionality or large combinatorial function. Never infer asynchronous memory into a design. It will use too many additional resources to give it its asynchronous behavior. The 18 kilobit block RAM can be organized in various aspect ratios, that is, words by bits. This means that data can be accessed in the most efficient format for your design. This reduces the logic to format data and eliminates the need for the user to build extra logic to change the data formats. Because the 18K bits are not a power of 2, the aspect ratios have some interesting settings, as you can see from this chart. Only 16K bits are available in the 1, 2, and 4-bit data formats. To make maximum use of the memory available, you can use wider formats, and we encourage you to do so. Don't be afraid of using the parity bit. It is really just another output to the block RAM. There is no dedicated logic to calculate a parity value associated with the block RAM. Note that the 36-bit output configuration prevents access to the dedicated multipliers that are physically located next to each block RAM, and therefore this should be used with care. So basically, keep in mind, if you're going to be going to 36-bit output from block RAM, you may lose access to the particular multiplier placed next to the block RAM. Memory can be inferred in HDL or via the core generator, but to gain the maximum control and tracking of such a valuable resource, it is often a good idea to consider using the Unisim library primitives directly in your code. This is an example of instantiating a Unisim primitive. Also note that if we used the core generator to build this memory, it would also create an instantiation template for you to use. In this case, we are using the 18-bit output of the A port and the 18-bit output of the B port. Note that each port width can be set independently. This is the configurable aspect ratio feature. And here we see an example of connecting a single 18-bit bus to the data in parity bits. The parity bits are just an additional couple of outputs, so there is no reason to keep them separate. The core generator software hides this kind of detail. One of the most important things to remember is that block RAM becomes a ROM if it is never written to. This means that block RAM can be used to replace any LUT function in any design. So in this example, there is a 10-bit address that is used to decode an 18-bit output. Essentially, a large complex decoder is created. Now, when you consider that the equivalent complex functionality would require many LUTs and create multiple levels of logic in the FPGA, this is suddenly a very helpful resource to saving those LUTs and to be able to pack more logic into the FPGA. To encode block RAMs in this way, remember that all the blocks can have their initial content stored in the configuration bit stream. So upon power-up, every block RAM is programmed. The challenge is writing the initialization string to initialize the 18K bit block RAM. It can get kind of big, and being that it's done in hexadecimal can be a little challenging. So try to use the block RAM for combinatorial logic. It saves a ton of LUTs. In this example, we have defined the initial values directly into our HDL code. Well, to be fair, this example only shows 4 lines out of the 72 lines that are necessary to initialize a single block RAM. As you can imagine, this is not very popular. In this next example, we have used the core generator to initialize a single block RAM. As you can see, it is not smaller, but it is a little more readable. You should know that if you don't initialize the block RAM, it will come out of configuration with initial contents of 0. So in this case, a reset would not be necessary. This is interesting because if we get in the habit of inferring the appropriate register, we can program the flip-flops to come out of configuration initialized to a particular state without using a global reset. So keep this in mind, because the more resets you avoid building, the more efficient and fast your design will operate. Okay, so now we have an exercise for you to complete. A Spartan-3 device is being used in a cost-critical design where there's a lot of pressure on the resources to fit in the device. The submodule you see here has a requirement for the memory shown. So we've got a 16-bit data in and a 16-bit data out, as well as a 12-bit address port. And we're supposed to accommodate 4K locations. So take a few moments and sketch your solution for the single port RAM for the 4K by 16. We're going to show you how your results can vary depending on the aspect ratios you choose. Again, one of the hidden benefits of using the core generator is that it chooses the best implementation, that is the best input multiplexer logic and output decode logic that is necessary. So this slide shows you the 4K by 16 memory. In this case, the wrong aspect ratio was chosen. Choosing the wrong aspect ratio can waste resources and hurt your timing. In this case, we're building a memory that requires 4 block RAMs. We chose to segment the memory so that only one of the block RAMs was being used at a time, so all 16 bits come from 1 block RAM at a time. This aspect ratio requires input decode logic, that is the AND gates on the left, and the output mux logic to be built on the right. This logic, of course, uses extra LUTs and adds input and output delay. In fact, this configuration would require 18 extra slices and get pretty expensive pretty quickly. So keep in mind, if you build this with a core generator, it's going to automatically choose the proper logic and the optimum logic to make this a fast implementation. This slide shows how choosing the correct aspect ratio solves everything. The 1024 by 16 memory is now making use of the internal multiplexing structure of the block RAM blocks so that no other logic is required. In this case, that is with a 4-bit output. So at every sample, each block RAM will contribute 4 bits to the output. This saves you from building any input decode logic. Likewise, the 16-bit output is wired together without any muxing. Block RAM memory can be inferred by a synthesis tool, but it is very unlikely that it would be able to build this. Or, for that matter, would you maybe want to trust it? I don't know. Fortunately, the core generator allows choosing the optimum configuration easy. So in case you start building memories without using the core generator, keep in mind the proper choice of your aspect ratio impacts the speed and the size of your design. Likewise, it's always useful to use spare block RAMs for something, especially if it saves LUTs and improves the speed of your design. The dual port functionality is also a terrific way to access the spare capacity of a block RAM used as a single port memory.